video. So we want to hit this last quadrant. And if you notice, we try to have like a logical progression. We started with reactions of alcohols, and then we talked about stayed with alcohols and talked about taking them and converting them into carbonyls. And then in the top right quadrant of the handout, we talked about reactions of carbonyls. And then in the bottom quadrant, this is still kind of dealing with carbonyl transformations, but it's just using a different or deriving a different type of functional group. So let me cut this out, and we're going to work on these reactions. We're going to start with the amide synthesis because it's the simplest out of all of these because we've already seen it. We've seen this when we did transesterification. And so that transesterification reaction, the amide formation mirrors that. And so we can mirror that reaction, then we ought to know be able to come up with a mechanism in order to make that happen. All right, so because that transformation is very, very similar to ester formation. You can see right here. And again, let me go back to something we've been talking about. I've said it multiple times. I can't stress it enough. Knowing your functional groups is the key to figuring out how these reactions work. If you are rusty on functional groups, I can't stress it enough. You got to go over that again and again and again, because none of the reactions make sense if you don't understand what functional groups are that you're transforming, or their polarity or their reactivity. None of it makes sense if you don't get that part. All right, so let's do the amide formation first. So we're going to take this, and I'm just going to rewrite it. And what's today? The 20. All right, so we're going to take the amide formation first. So notice what we're starting with the amide formation. And you can see right here, again, knowledge of functional groups is critical. This is your amide. You have a carbonyl. Sorry, wrong pen. With a bond, a single bond to nitrogen. So it's an analog of a carboxylic acid. So this is an acid, and we've seen that we could take that acid and turn it into an ester if we react the acid with an alcohol. So now we're going to make the analog, which is to react it with an amine, right? And this can be, it's too thick. You know, this nitrogen has a lone pair here. So the amine can be primary or secondary. And just to give you an example of a primary amine, this would be something like this. Where it only has one bond to carbon, so this would be primary. And then secondary, as you can imagine, would be something like this, right? So this is secondary. Got two bonds to carbon. So primary, secondary means both work. And in this case, we're going to just go through the mechanism. So let me take that acid, and it can be, that R group can be anything. I'm just going to leave it as an R group. And then let's just make this methylamine. All right, so somebody help me out. I have an amine. I have a carboxylic acid. Which one of those do you think is the nucleophile? Again, let me go back to something else I've been stressing in this whole section. All of this chemistry we've seen before. It's nucleophile, electrophile chemistry, or acid-base chemistry. And all of that we learned in part 1. So which of these two do you think is the nucleophile? We've been talking about carbonyls, and every instance where we've had a carbonyl, that carbonyl has been what? Nucleophile or electrophile? All the instances that we've looked at so far. Anybody?
Electrophile.
It's the electrophile. And the reason it is, again, going back to functional groups, got to know this. This has to be kind of etched into your brain at this point, that a carbonyl is, I'm gonna put some long pairs here. This is partially negative. That's partially positive. So if you put that in the presence of any type of nucleophile, that nucleophile is going to attack the carbonyl carbon, right? So the amine over here, that's obviously, if this is my electrophile, then that means that the amine here is my nucleophile, right? So the attack is always the same, source to sink, just like we learned in part 1. So I'm going to take this pair of electrons and attack here. Normally, when you do this, is just like the transesterification, you'll have to catalyze it. So you'll react this with a proton source to activate your carbonyl. Didn't try to do that, sorry. Right, so you really would have something like this, where now that's protonated and with a plus charge. So it makes it just facilitates the reaction. So just like when we did transesterification, this is normally an acid catalyzed reaction as well. So we've seen that before. So we attack the carbonyl, and then in doing so, we also have to break the carbon-oxygen pi bond. And then what happens when we attack a carbonyl with a nucleophile? What is that common thing that we always get? Anybody remember that?
Is it the tetrahedral intermediate?
Tetrahedral, excellent. Tetrahedral intermediate, which is going to look in this case like this. So that's R1, and then this is N, H, H, CH3, and this is now positive, right? Formal charge is another thing that we always have to think about when we're doing these types of reactions. So let's just say for the sake of our discussion, we need to get rid of that, right? Because if you look up here, let's go back, and I apologize in advance for all the scrolling back and forth. But look what I did. I took the OH and I swapped it out with the amine. All right, I swapped it, and I'll clean all this up before I post these notes to Blackboard. But I swapped it out with the amine. Is that a substitution?
Yes.
Can you do substitution on an sp2 carbon like a carbonyl? We cannot. So it is an addition followed by an elimination. We talked about that already, right? So all these transesterifications and amide syntheses all follow the same pathway. You add to the carbonyl, and then you eliminate some leaving group. And in this case, it's going to be, what do you think? If I want to get rid of the OH, what's the easiest way to do that? This is all stuff we learned in part 1. And I want to make everybody in here happy, right? So my job is to get rid of charges and make sure everybody has an octet, all that good stuff. So how do I get rid of OH? Is it just going to leave on its own?
No.
What would you do to you?
Okay. So I was thinking proton transfer.
You want to do a proton transfer. You having a functional group right there, the ammonium ion that's adjacent to the OH group. That proton is very acidic, and proton transfer is a logical next step, right? Because what you want to do is get rid of, and let me bracket this in because this is an intermediate. This is and this is going to look different for every carbonyl, right? That's my tetrahedral intermediate. And so now that intermediate gives rise to another intermediate where I have a hydronium ion that I need to lose as a leaving group. So this is going to be O, H, H. Now that's positive. This is N, H, CH3, and then this is my R group that was already on the acid. All right. So now I need to get rid of water, which is a great leaving group. That's something we've already talked about when we did. Now, the principles that we studied during substitution and elimination don't change, right? Good leaving groups are good leaving groups, bad leaving groups are bad leaving groups. But in this case, you cannot just simply substitute on that sp2 carbon. You have to add and then eliminate. So I want to get rid of that water. When we did transit esterification, what did we do to get rid of water on it from the intermediate? Anybody? Don't I need my Pabon back because I'm trying to get to the amide?
Then you add the conjugate base. Or,
Well, not yet. You're right. We're going to use that at the end, but right now I need to just eliminate. So I'm going to put this Pabon right here. I'm going to put it back. I'm going to put that back. So the way I do that is just to use that pair of electrons on oxygen and push those between the carbon and oxygen to reform the carbonyl. And then I'm going to kick off water or eliminate water. So that's going to give me this. I'm going to have this. That's positive. And you can see right away, I'm going to put the nitrogen over here. And this is R1. You can see right away now, and this is plus what? Plus water. All right, and you can see right away now that we've lost water as our leaving group. So this is the elimination step to get me almost home. But now, Tia, you said something about using a conjugate base, and you're right. So if this is acid catalyzed, that proton that was right here came from somewhere, right? It came from some acid, right? So the conjugate base of that acid can come in now and pull that proton back off, reform the acid, and then the acid can go and catalyze another reaction. So I could just write this as, because we've seen this before, I'm not going to go through all the nuts and bolts of it, but this can come in and just do a proton transfer here, right? So that'll get me to my amide here. Sorry. So that plus and H2O plus my acid, whatever acid I started with. And you have to remember that if that acid is a catalyst, and let me just put it here, right? If it's a catalyst, at the end of the reaction, it's going to get reformed.
I have a question.
Go right ahead.
Okay, so, oh, wait, never mind.
Light bulb. That's good. That's good. All right. And any questions about the reaction itself? If you recall, when we did the transit esterification, this is the exact same mechanism. The only difference is we're not using an alcohol. We're using an amine, right? In this case, a primary amine reacting with a carboxylic acid. But the mechanism is identical. You add to the carbonyl. That's the first step. You form a tetrahedral intermediate. You do proton transfer, and then you eliminate. Those are the exact same steps that we did when we did the transit esterification. All right. Any questions about that? All right. Let me add another page, and then we're going to discuss now another reaction involving amines and carbonyls, and that is the formation of what we call a shift space. Did y'all do this reaction in lab this semester? Where you made shift spaces in organic 2 lab?
I don't think so.
Y'all didn't discuss it at all? It was like, it wasn't like a part of, because normally this is one of the big reactions that we do in part 2 is amine formation, because we had a project where we would take the amines and use them as ligands on metal complexes, but maybe they stopped doing that. right? We're going to talk about it here. All right, let me show you what happens first. Then we'll discuss the nuts and bolts, and then we're going to go down and work through an example where we'll put the arrows in. Right, we're going to still work through the arrows here, but I have an example in this handout where you actually have to insert the arrows to show each step, the progression of the mechanism in each step. Right, so let me put a lone pair here. Sorry about that. Right, so, you know, nitrogen is always going to have that lone pair. Right, and again, I'm using an aldehyde. I can also use a ketone. And this, in order to make an amine or Schiff's base, right, that's another name for that compound, Schiff's base. In order to do that, this has to be primary. There's a reason for that. You'll see why in the mechanism. Both of these protons are involved in the mechanism. So they both get removed. If you'll notice in the product, and I'm going to show you this kind of like we discussed the Vidic. I'll show you a way to predict the product without even if you don't know the mechanism, you can predict the product. But at this point, we should be kind of well versed in, you know, identifying nucleophiles and electrophiles. All of these reactions, I try to keep this consistent. All the reactions that we've done, excuse me, have involved the carbonyl as an electrophile, and then whatever is reacting with it is your nucleophile. So with this reaction, you need a primary amine, and this can be an aldehyde or ketone, but in this case, we're going to use aldehyde. Right, it can be aldehyde or ketone, doesn't matter. All right, but that carbonyl, the dipole is always going to be towards oxygen. So the carbonyl carbon is susceptible to attack by a nucleophile. So this reaction, notice what the outcome is. Before we even talk about the arrows, look at what I did. This is almost, well, it's not identical, but it's similar to kind of like the Vidic, what we looked at earlier, like the thought process behind it, right? I have replaced the carbonyl oxygen with the nitrogen of the amine, right? So think about it this way. If I have an amine, a primary amine, think about me adding this. Whatever that is, right? Whatever is the R group is on the nitrogen and the nitrogen itself. And I'm going to basically plug off the carbonyl oxygen, which doesn't happen like that. You know that. We're going to have to eliminate it some type of way. But we can remove it and replace it with the nitrogen. You can see that over here. Both hydrogens are gone, right? So when you make the amine, both of those hydrogens are involved in the mechanism. And if somebody can tell me how you think we get rid of the oxygen, I'll buy you lunch. How do we get rid of oxygen? What's the most facile and easiest way to get rid of oxygen in a reaction, like especially the reactions we've been looking at? I need my Jeopardy music. All right, don't worry about it. We're gonna, when we get a little further in the mechanism, I'll open that door back up. All right, so now let's look at what happens. Obviously, we're going to attack, excuse me, the carbonyl, like so. What am I going to get as a result of that?
Tetrahedral intermediate.
Tetrahedral intermediate, it doesn't change. That's, I keep repeating that because I'm trying to drive home the point that anytime you attack a carbonyl, you're going to generate this intermediate. It's not going to be the same in each case, but the structure is going to be the same. right? So I'm gonna just try to keep this here. That's negative. I'll keep the hydrogen pointed up. And then here is my amine. And let's make our CH3, right? I want to get rid of oxygen. I'm gonna ask the question again. Lunch is still on the table. I want to get rid of oxygen. What can I do to oxygen to make it leave? All right. Notice I said both protons in the amine are involved in the mechanism. So now I have to buy myself lunch. All right. So that's both protons involved, and both of them end up getting transferred to oxygen to turn it into water. Right. That's the easiest way to get rid of oxygen in these particular cases, where you can always eliminate it as water. If you can protonate it or do a proton transfer with it somehow by adding in some acid or putting a functional group nearby that has acidic protons, you can make it into a hydronium ion and cause it to leave as water. So let's see what happens. So now I'm going to actually do two proton transfers separately, right? So I'm going to do that. That's one. That's going to get me to, and let me bracket that in. That's going to get me to this intermediate. If you notice, there are several intermediates in these reactions. And if you think about that, if I ask you something about the energy diagram for one of these reactions, it would basically have multiple valleys, right? Because the peaks show where you go from reactants to transition state, and then the valley is an intermediate. So to have multiple intermediates on the way to product. Some of them will be long lasting, some of them won't be, but the point is that you'll see them. All of these are, you can isolate them, all right? And if you can isolate them, then you can propose it, excuse me, as a part of the mechanism. All right, so that's that. Now, again, I want to get rid of water. What would you do? I need another proton on oxygen, and I'm not using proton from an outside source. Actually, this reaction, you actually do this in the presence of a desiccant. You'll do it in the presence of like mag sulfate or some desiccant that absorbs water, because water is one of your side products. And so according to Le Chatelier's principle, if you have a desiccant in and you make water, but it gets absorbed immediately by the desiccant, that's going to force the reactant side to produce more water, right? So it's kind of like it's a way to facilitate the reaction by adding in a desiccant. So normally you'll see it done in the presence of mag sulfate or sodium sulfate or some other desiccant like that. How do I get water from this intermediate? What can I do?
Would you do proton transfer with the other hydrogen?
We'll do another proton transfer, right? And then I'm going to end up with another intermediate, but this time I have a hydronium ion. Right, and this is positive, and then this was H, and this is N. Now N is negative. Now what? We've seen this before. When we did the hemiacetal formation, you got a functional group next door to a leaving group with a pair of electrons that can donate. What did we call that? Anybody remember?
Iliad.
Well, no, this wouldn't be an iliad because the charges are separated by one carbon. That's I like the thought process, but this is not an iliad. It would be an iliad if the oxygen and nitrogen were bound together and one was positive and one was negative, but that's not the case here. What would be iliad like? But what did we talk about when we did hemiacetals and acetals and we needed to get rid of water? Remember, for the acetal formation, we came up with two pathways. One of them was where water just left spontaneously, and the other one involved what? Anybody? I'll open the door back for lunch if you can tell me that. Right, remember we talked about neighboring group participation? So if I push this pair of electrons here, it's going to force water out, right? So that's going to get me to my amine. This is in CH3H plus water, right? So this is a this reaction involves multiple intermediates, but the intermediates all have some type of proton transfer involved in order to remove water or eliminate water, right? So this is your elimination step. So elimination, and then we had addition followed by proton transfer. Then we had another proton transfer. Right? And then followed by our elimination. Any questions about this mechanism or about this reaction? So we'll come back to Gabriel synthesis because I actually want to take what we already looked at and apply it right away. That's the best way to kind of make this stick. So let's go down to here, right here, and let's see if we can put the arrows in for this mechanism. All right, it's a very similar reaction, just different start materials, but the mechanism doesn't change. If you have a primary amine, you have an aldehyde or a ketone, you can make an amine, right? Same mechanism. So what is the first set of arrows you're going to put in here?
The amine attacks the carbonyl carbon.
Right here. Here, is that right? To here?
Yes.
All right, so that'll get us to this stage, which is what? What do we call that? It's not boxed in.
So,
Go ahead.
tetrahedral intermediate.
That's our tetrahedral intermediate. And this actually stays at that point until you eliminate, right? So you have multiple intermediates. That's one of the hallmarks of this reaction is that you have this tetrahedral intermediate that does 2 proton transfers followed by an elimination. So let's look at, so now we're going from here to here. What happened? And really, if I give you the structures like this, it's just logic. You're looking at what you have versus, so what you have here and comparing it to what you have here to see what changed. And that can give you an idea of what to do with the arrows. Let me put the electrons back in. All right. So how would I go from, let's just label them. We'll call that A. How do I go from B to C?
You do proton transfer.
Proton transfer. Is it, let me ask this question from the other day. Is it inter or intramolecular?
Intra.
It's intramolecular, right? Because it's happening within the same molecule. And what you'll find out when you're doing any type of science, especially chemistry, knowing terminology and knowing nomenclature and things like that is critical. Just like knowing your functional groups is critical, right? So that those little terms and phrases that describe certain processes, that's really important to know as well as knowing how to do the reaction. So this intramolecular proton transfer to get me to C. How do I get from C to D? Let me put the electrons back in.
You do another proton transfer.
Do another. We just saw this, right? So, I mean, we're going to do another one here. Boom, like so. And that's going to give, did I put a pair? I'm going to put a pair of electrons here. That's going to give another pair of electrons to nitrogen to get us to D. Right, and now this is to get from D to the product. What would you do?
This is this when you do the neighboring neighboring.
It's there. Yeah, you're right. It's neighboring
Yeah.
group participation.
Yeah.
So we're going to take this and do here like so, right? And that's going to kick off water, which I don't have drawn here, but we can write it in and give us the amine, right? And amine chemistry is simple to do. These reactions, normally you do them at room temperature. Again, you take your primary amine and your carbonyl source, ketone or aldehyde, you add in some mag sulfate as a desiccant, and room temperature, let it stir, go to lunch, come back, boom. Go ahead, Tia.
I have a question.
Yeah, sure, go ahead.
So with the amide synthesis and the amine formation, I noticed one has the acid catalyst at the end and one doesn't. Like, how would you know when that will occur?
Well, okay, so with the amide synthesis, look at what we started with. So with amide synthesis, we started with a carboxylic acid, right? That's a lot less reactive than an aldehyde.
Okay.
And that carbonyl carbon is less reactive than an aldehyde because of the electron density here on this oxygen, right? Because you can do resonance with that carboxylic acid, the hydroxyl group, right? You can do resonance here like that. So it kind of ties up the reactivity of that carbonyl. So you have to add in an acid to kind of facilitate that. But the aldehyde, that's why for amides, if you want to make an amide, you use a carboxylic acid. If you use an aldehyde or a ketone, the amide formation doesn't happen, right? It's easier to make the imine than it is to do the amide. Because with an aldehyde, think about it this way too. What would you eliminate from the aldehyde? Like what group would you eliminate in order to make a amide? Neither one of those are good leaving groups. The hydrogen is a terrible leaving group. Carbon is a terrible leaving group. And so you look at the functional groups. If you start with a carboxylic acid and an amine, you're going to get an amide. You start with a aldehyde or ketone and an amine, you're going to get the imine. And that's really the difference in the reaction.
Okay.
Right? It's what you start with. If you start with an aldehyde or a ketone and a primary amine, it's going to give you the Schiff's base or the imine. Start with the acid, it's going to give you the amide. So the carboxylic acid starting material, you should be thinking in terms of like transit esterification. It's the same process. It's just a different nucleophile added to that to the acid. Turn this ringer off. Sorry. All right. Any other question? Okay. I think the last reaction here is Gabriel synthesis. And this is a fairly common reaction. Let me just copy that and paste it down in another section. Yeah, I can post it here. Right, so with Gabriel synthesis, this is a way to make amines. Right, this is a way to synthesize. You can make primary or secondary amines. Right, And with the Gabriel synthesis, it's fairly easy to spot. And again, we have to get in the habit of, even if we don't know all the arrows, we can still predict the product. And the way you predict the product is to look at the functional groups that are reacting. So when you're doing Gabriel synthesis, it's always the same start materials. It's phthalate, which is this compound right here, and alkyl halide, and a base, right? Those are your three main start materials. So with phthalate and the alkyl halide, you can already see, and then look at the product. I have it color coded here, where the R group on the alkyl halide, let's just say it's a CH3. Let me keep it the same color. Right? That R group is now here bonded to this nitrogen. Right? So even if you can't figure out all the arrows, you can predict the product. Whatever alkyl group is attached to that alkyl halide is going to end up on your nitrogen. Right? And this is again a way to make primary amines. You can also make secondary amines if your alkyl halide is secondary. So let me put that up here. So a primary alkyl halide will give you a primary amine. Hold on, let me just write that out because that's going to confuse you. A secondary alkyl halide will give you a secondary amine. Can't make tertiary amines this way, but you can make primary and secondary. All right, so let's walk through the first initial part of the mechanism. Right, so for here, I'm going to redraw phthalate, even though I could just steal it, but I won't do that. Normally I would, but so this is phthalate. Right, and I'm going to treat this with the base. Right, the base is going to be used to pull off this proton. Now keep in mind, I do have a lone pair here already, and I'm going to treat that with KOH. And you know this is a salt, K plus, OH minus, very strong base. And all I'm going to do is a proton transfer here. And again, every time we go through one of these mechanisms, I can't stress it enough. None of this is new. The reactions are new, but the processes and the mechanisms are the same as we learned in part one. This is just acid-base chemistry. You have a base, the phthalate proton is acidic, and we're going to make this. So that's the salt there, right? And then plus water, right? Because the proton that came off of phthalate is now going to end up with the hydroxyl group, right? So now this is my nucleophile, and I'm going to react that with the alkyl halide. So I'm going to say this is CH3I, right? This is, again, stuff that we've already learned. The first step was an acid-base reaction. This is going to be just a simple SN2 substitution, where now this is going to attack here. And let me draw this out. Like so. Simple. This is all stuff we've done before, right? So now my phthalate is substituted with that methyl group. So I'm here now. right? So that's that. Plus, let's get the side product so we can follow and track what's happening. So plus Ki, because that is going to form a salt when iodine leaves with those long pairs. It's going to be negative, so it's going to be K plus, and then I minus plus water, which we made in the initial step. Now the next step, this is the crucial part right here. The next step is just popping the phthalate open. So you can flood this. Basically, you just run a reaction in water, or you can add in some other source to attack these two carbonyls and to protonate your nitrogen, right? And so at the end of the day, you're going to end up here. So you'll end up here with this diacid, and then you'll end up with your primary amine here. All right. So with the Gabriel synthesis, I'm not really concerned about you knowing the mechanism as much as I am you knowing the outcome of the reaction. All right. So that final step is ring opening. All right. So you have proton transfer in the first step, followed by SN2 substitution, followed by ring opening. Right. But the goal is here to make this amine, this primary amine. So this is one of your tools in your toolbox to make primary amines. Let's do one more. I think one more example, because I have an example. Any questions about that before we move forward? All right, let's go to this example. Where is it? Here. All right. Look at the amine that I have, because it's asking for the star material. Here's the amine that I have right here. The phthalate has already been deprotonated. And then sodium hydroxide and water for that second step to pop the ring open. What alkyl halide did I start with? That's the question. And how do I know where to put the halogen if this is the primary amine that I got in the product? Anybody? Let's go back up to here. What did I do to the halogen in this SN2 step? Can you see what happened? I attacked it and lost the halogen. And so the alkyl halide is going to be basically the nitrogen replaces the halogen. It substitutes for it. It's not a direct process, but you can see that in the end, where the halogen was, now you have that nitrogen. So we go back to here, right? What alkyl halide would you start with? Having the amine in hand already and knowing that what the process is to get there. What alkyl halide would you start with? Anybody? Put lunch back on the table. The third time I'll try to buy somebody lunch. Go ahead.
The primary.
Would you? Yeah, it is primary. I agree with that. But what does it look like? That's the question. What's the structure of it? That's the point, the question I'm trying to get to.
Right.
Would it look like this? Can you see that this halogen now is what eventually gets replaced by nitrogen? All right, so I would start with that. All right. And then in the next step, I have a primary amine and I have a ketone. What's the product of that reaction? All I'm asking about is predicting the product. I'm not even asking you to show me the arrows. What happens when you take a primary amine and a ketone and you stir them together? in the presence of a desiccant like mag sulfate?
You know, would it be an amine?
You're saying, are you saying an Emmy like this?
With yeah, yeah.
Okay. Yeah, you're right. And then this is still attached, right? Now all that's still attached to the nitrogen. You don't lose that group. You lose the hydrogens, but not the alkyl group, right? So again, this is an example of how you would combine these reactions, right? You make your primary amine, and then you can take it and use it for some other process like amine synthesis. And that's why the reason why we do that is to kind of illustrate that anytime you're doing chemistry, you always have an end goal in mind. You don't just do reactions just for the heck of it. Everything has a purpose behind it. So if I'm making primary amines, then that means I'm going to use it for something, right? In this case, we used it for amine synthesis. All right. Any questions about anything before we log out? All right. Check later for the announcements, and I'll make sure that let me stop recording.